Hello, and welcome to Linear Algebra. This is lecture 15, and our topic today is bases. So last time, we talked about linear independence. And I mentioned that we will call an ordered set of vectors a list of vectors. So I just thought I should write that out explicitly. This time, we'll be talking about bases. So these are linearly independent spanning sets, as we'll see. Okay, so start with a definition. A vector space V is finite dimensional if there is a finite list of vectors in V that span V. Okay, so that's what it means to be finite dimensional. If a space is not finite dimensional, we say that it is infinite dimensional. Right, of course, we prefer not to include redundant vectors. So we'll say that a list V1 through N inside a vector space is a basis of V if it is linearly independent and its span is all of V. Okay, so for example, the canonical basis of Fn is a basis of Fn. Good thing, since we're calling it the canonical basis, right? And it's easy to see that it's a basis, right? We've already seen that it spans all of Fn, and it is very quick to see that it is linearly independent, right? For example, our algorithm says make a matrix whose columns are the elements of your set and put it into reduced row echelon form. If every column has a pivot, then the set was linearly independent. But in this case, if you make a matrix whose columns are the elements of this set, you get the identity matrix. Okay, here's another example. Let's let curly P n of R be the space of all polynomials of degree less than or equal to n and real coefficients. Then the list 1, x squared, so just the monomials up to degree n is a basis PNR. Okay, so that's the same as saying that it's linearly independent and its span is V. Right, so in this case, that second part is very easy, right? To say that the span of this list is this set is to say that every polynomial of degree n can be written as a linear combination of these vectors, of these polynomials. But that's trivial because every polynomial of degree n can be written as a sum of multiples of these monomials. To say that it's linearly independent, well, you could check this just like we did last class when we were working with the continuous functions of 0, 1. If you take a linear combination of these and you want to see if setting that equal to 0 implies that all of the coefficients are equal to 0, well, remember, when you set it equal to 0, you're setting it equal to the polynomial 0, right? So, okay, you can evaluate at 0, for example, to get the first coefficient at 0. You can differentiate and evaluate at 0 to get the second coefficient equal to 0, and so on. Differentiating and evaluating at 0 will show you that all of the coefficients have to be 0, right? And so the only linear combination of these that gives you the 0 polynomial is the one with all of the coefficients equal to 0. Okay, of course, there are many other things you could do to see that the coefficients have to be 0. You could just notice that you have n plus 1 points where it's 0, then the polynomial has to be 0 because any polynomial of degree n has at most n real roots or is a 0 polynomial. Okay, here's another example. The kernel of a matrix. A matrix size n by n is finite dimensional. And it is easy to find a basis. Just solve ax equal to 0. So by this, what I mean is that we already have an algorithm for solving ax equal to 0, right? We do Gaussian elimination. We find that variables are either free variables or pivot variables. We write the pivot variables in terms of the free variables, and that gives us an expression for all of the vectors in the null space, or all of the solutions to this equation. Well, the claim is that that also gives you a basis of the null space. So let's do an example, just to show you what I mean. So if you take the matrix with columns 2, 2, 1, minus 1, 0, 1, 3, 2, 0, and minus 5, minus 4, minus 1, then the reduced row echelon form, when you've augmented with the 0 column, is the matrix with columns 1, 0, 0, 0, 1, 0, 1, minus 1, 0, minus 2, 1, 0, and then 0, 0, 0. And so vectors in the kernel of A satisfy, right? So what we do is we translate this back to equations, and then we see here that x and y are pivot variables, z and w are free variables. So the vectors in the kernel satisfy x, y, z, w. Well, x I can write in terms of the free variables as minus z plus 2 times w. Y is a pivot variable. I write in terms of the free variables as z minus w. Z is a free variable, so it just remains z. W is a free variable, it just remains w. And so now I can write this as the multiples of z. So I get minus 1, 1, 1, 0. And then the multiples of w, and I get 2, minus 1, 0, 1. Right? So here with z and w free. Okay, so here we go. This is a spanning set for the kernel, right? And in fact, it is a basis. So here I'll write. Thus, the kernel of A is the span of these two vectors, minus 1, 1, 1, 0, and 2, minus 1, 0, 1. And since these vectors are linearly independent, right? So how do we know that? Well, for example, look at the last two entries. Okay, so let's stare at these last two entries, right? Notice that if you look down here, you end up with like a little identity matrix, a 2 by 2 identity matrix, if you were just to focus on the last two rows of these columns. Okay, so why does that make it really easy to see they're linearly independent? Well, let's say that you had a multiple of this vector, a multiple of this vector, and then you add them together and you get the 0 vector, right? Well, what can you say by looking at the third coordinate? Well, the third coordinate would just be the coefficient of this vector, because over here you have a 0, so its coefficient is not going to contribute at all. So just knowing that the third coordinate is equal to 0 of this linear combination would tell you this coefficient has to be 0. Same thing if I look at the fourth coordinate. The fourth coordinate just has a multiple of this coefficient, and it doesn't have any contribution from this vector at all. So just by looking at the fourth coordinate, I know that the coefficient of this vector has to be 0. So if you give me a linear combination of these two vectors, and it's equal to the 0 vector, then I can just stare at the third coordinate and tell you that this coefficient has to be 0, stare at the fourth coordinate and tell you this coefficient has to be 0, and so the set is linearly independent. Right? And this is always going to happen when you find the kernel using Gaussian elimination and our algorithm for finding solutions, because the free variables are always going to just have a 1 and then 0 for the other free variables, right? So just by looking at the rows corresponding to each of the free variables, you'll find that those vectors you wrote down are linearly independent. So our usual way of solving AX equal to 0 produces a basis for the null space of a matrix, right? So it's always easy to find a basis for the kernel of a matrix. Okay. Okay, so let's summarize a little bit of what we've seen in this special case of Fm, right? So given a list of vectors, v1 through vn, in Fm, so this very special vector space, we've seen that, okay, first of all, this list is linearly independent if and only if the reduced row echelon form of the matrix you get by putting these vectors as columns has a pivot in every column. Okay, so in particular, we must have n less than or equal to n. Right? If you have a pivot in every column, well, every row can only have one pivot. So you must have at most as many columns as there are coordinates, as there are rows. On the other hand, if this list of vectors spans Fm, then that's the same as saying that the reduced row echelon form of this matrix has a pivot in every row. right? Because remember, what you want to think about is, if I were to take this matrix, call it A, if I wanted to solve AX equal to B, then these columns span FM is the same as saying that I can always solve AX equal to B, right? I can always solve AX equal to B means that the system is always consistent. The system is always consistent means that if I form the augmented matrix and put it into reduced row echelon form, I never have a pivot in the final column. The only way I can guarantee that for no B is there a pivot in the final column is if every row already has a pivot before you put the vector B, right? That is, every row in the reduced row echelon form of A already has a pivot. In particular, that means that n is greater than or equal to m. So I need to have at least as many columns as I have rows if I'm going to guarantee that every row has a pivot. Putting these together, we see that a list of vectors is a basis of Fm if and only if the reduced row echelon form of this matrix is the m by m identity matrix. Okay, very good. So let's take the definition of basis, and we're just going to re-express it a little bit. So the theorem says that a list of vectors, v1 through vn, is now in an arbitrary vector space, is a basis of V if and only if every vector W in V can be written in a unique way as a linear combination of the vectors in this set, v1 through vn. Okay, proof. Okay, it's an if and only if, which means that to prove it, I should prove both directions. I need to prove that the first hypothesis implies the second, and that the second hypothesis implies the first. So let's start by proving that way. So I'm going to assume that I have a basis, and I want to show that every vector can be written in a unique way as a linear combination. Okay, so suppose that this list is a basis. We need to show that every vector W can be written in a unique way as a linear combination. Okay, so what do we know? We know that it is a basis. That's the same as saying we know that it spans and we know it's linearly independent. Okay, so since the span of the V's is all of V, we can write W as a linear combination. So all we need to check is that there's only one way of doing it. There is a unique way of writing W as a linear combination. Okay, but whenever you want to show that something is unique, standard thing to do is to take two different ways of doing it and show that actually they're the same. So let's suppose I can write W as A1, B1 plus dot 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 plus AN, BN. And I have W as A1 prime, B1 plus dot 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 plus AN prime, BN. Right? We want to show that AI is equal to AI prime for all I. Right? So assume I can write it as a linear combination in two ways. I want to show that those aren't actually two different ways. There's just one way. Okay, so what we can do is subtract these two equations. Right, so subtracting, I end up with the zero vector on the left, and on the right, I have A1 minus A1 prime times V1 plus dot 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 up to AN minus AN prime times VN. Okay, fantastic. We're in really good shape because on the right-hand side, we have a linear combination of the VI's, and it's equal to the zero vector. Okay, but if you have a linearly independent set, then the only way you can write the zero vector as a linear combination is the trivial way. All of the coefficients have to be zero. So by linear independence, we know that all of these coefficients, AI minus AI prime, is equal to zero for every I, and that's what we wanted to show. Right? So we started with two possibly different ways of writing W as a linear combination, and we saw that in fact they have to be exactly the same. Okay, so that proves one direction. Let's prove the other direction. So for the other direction, now we're going to assume that every vector in V can be written in a unique way as a linear combination of the set. We want to show that this set list is a basis of V. Okay, so to show that something is a basis, we need to check two things. We need to check that it spans and that it is linear independent, right? So, i.e., we want to show that the span of V1 through Vn is V, and that V1 through Vn is linearly independent. Okay, that it spans is obvious because we're saying that we can write every W as a linear combination. So it clearly spans. So just need to check linear independence. Okay, now I mentioned already before that almost every time when you're asked to check linear independence, you start the same way. If you want to show that a set of vectors is linear independent, what you do is you use them to write zero as a linear combination. And then you show the coefficients have to be zero. Okay, so all of these proofs are always going to start the exact same way. Assume zero is a linear combination, and then show that the coefficients are zero. Okay, so assume zero is a linear combination, A1, B1, AN, BN. We need to show the coefficients are zero. Okay, now since we also have zero is equal to zero times V1, right? Since we have the trivial way of writing zero as a linear combination, where we just put all the coefficients equal to zero, then since there's only one way of writing, so let's say by assumptions. So then, since by assumption, there's only one way of writing 0 as a linear combination, of this list, V1 through Vn. Right, so remember, we're assuming that every vector W can be written in a unique way as a linear combination, right? Well, 0 is a vector in V, so our assumption says that it can be written in a unique way as a linear combination. Okay, so we have the one we're assuming, and then we have the trivial one, but since there's only one way of doing it, the way we assumed must be the trivial one. So we must have AI equal to 0 for every I, and that's what we want to show. Okay. Now, great. So that's just a different way of writing what it means to be a basis. Next, we want to guarantee that we can always find a basis. Well, we can always find a basis if we have a space, a finite dimensional space. So suppose V is a non-zero vector space. If we can find a list V1 through Vn that spans V, then we can find a sublist. So a sublist, of course, just means a subset with this, with the same, where they're in the same order as they were in the bigger list. So we can find a sublist that is a basis. Okay, so anytime you have a spanning set, you can always extract from it a basis. Okay, and we'll prove this by an algorithm. So we'll just say how we do it. Okay, so we'll start with B equal to the empty set. We're going to add or not a vector to B so that at the end we end up with a basis. Okay, so step one. If V1 is not 0, then add it to B. So at the end of this step, note that either B is still the empty set, or B is the list with one element, V1. Okay, step two. If V2 is not in the span of V1, then add it to B. Note that at the end of step two, either B is the empty set, or the span of the elements in B is equal to the span of V1, V2. Right? Because either B is the empty set, or B has V1, or B has V1 and V2. Right? If B has V1 and V2, then obviously the span is the same as the span of V1, V2. If B is not the empty set and it's not equal to V1, V2, that means that B just has the vector V1, but also that means that V2 is in the span of V1, because otherwise I would have put it into B. So the span of V is equal to the span of V1, V2. Okay, so keep doing this. So this, what I mean by keep doing this, the jth step, what you do is you say if the jth vector is not in the span of v1 through vj minus 1, then add it to b. And note that at the end of this step, either b is the empty set. How could b be the empty set? Well, what if all of these vectors so far are the zero vector? You just have the zero vector repeated over and over again. Well, then I haven't added anything to b. But if you have non-zero vectors, then b will not be the empty set. So in which case, it's guaranteed that the span of b is equal to the span of all of the vectors from 1 to j. Okay, so then you keep doing this, and then after the nth step, right, where remember I started with n vectors, right? So at the nth step, I've now looked at all of the vectors. We've constructed b, right? So all we're doing is at every step, we're just deciding, does this vector add anything to the ones I already have as far as linear combinations go? And if it does, we keep it. If not, we throw it away and we look at the next vector. After the nth step, we have constructed b, satisfying that the span of the vectors in b is the same as the span of v1 through vn, which by assumption is all of the vector space v. Moreover, the linear independence lemma guarantees that b is linearly independent. So b is a basis. Right? In particular, we see that every finite dimensional vector space has a basis. Because being finite dimensional means you can find a finite spanning set, and then this algorithm says you can extract from that a basis. So in particular, for the vector space Fm, there is a better version. Of this algorithm, if you give me a set v1 through vf inside Fm, we can find a basis of the span of these vectors, still calling it B, by putting the matrix v1 through vn into reduced row echelon form, and then including bi in B if and only if the ith column has a pivot. Right, so we've talked about this already before. So let's just notice that this picks out the exact same vectors we would have picked out if we had followed the algorithm, the n-step algorithm that I mentioned previously. So let's say, indeed, if this matrix is already in reduced row echelon form, then our n-step algorithm would pick out the columns that have pivots. Because, for example, if Vj does not have a pivot, then that means that every non-zero entry in that column has is in a row where there's a non-zero entry before that to the left, right? So, but that's the same as saying that I can write this as a linear combination of the previous columns. Right? But now notice that this relation is equivalent to knowing that the vector of coefficients here, C1 through Cj minus 1, is a solution to the system with augmented matrix having the vectors v1 through vj minus 1, and then adding vj. And whether or not this vector is a solution is unchanged by row operations. So the two algorithms pick out the same sublist. Of v1 through vn. Okay, so we'll stop there and pick it up from there next time.